Okay, so let's really focus in on these equilibria systems. So we'll talk about weak acids first, and then we'll talk about weak bases next. And so the first thing is, for weak acids, KEQ becomes Ka. So A stands for acid. And in general, it's going to go something like this. You're going to have something with an H and then a counter ion, which we'll just call A for acid. And, that's aqueous. So, this could be like, CH3COOH, in which case A would be acetate. It would be the acetate ion with an H on it, giving you acetic acid. And this is going to react with water. And it's a weak acid, so we're going to get an equilibrium. And we get the counter ion, A minus. And then we're going to get the hydronium ion. We're making hydronium, it's an acid, right? It's donating the H plus to water to give us H3O plus. So this is just a very general form. It's also present in your book, but this is a pretty universally accepted way. We'd call this a monoprotic acid because it only gives up one H plus. Next week we'll talk about polyprotic acids, like what if it gives up 2 or 3 or 4, which doesn't happen often, but there are some that do. And so that can be more complicated. So for now we're just sticking with a system where we can only give up one H plus. Okay, so monoprotic, one proton. H plus is a proton, right? Like, there's just a nucleus with a proton, no electron around it, H plus. So that's where the name comes from. Now if we write out our expression for KEQ here, or as we're now calling it, Ka, we will have our products over our reactants. So we'll have our concentration of A minus times our concentration of H3O plus, all of which is divided by a concentration of HA. And once again, we ignore water because it's a liquid. Alright, so that's our expression for Ka, and that's going to equal some number. So often what you can do is look in the back of your book. There's a table of values. You can get Ka values for different weak acids. And if it is a polyprotic acid, you'll have like a Ka1, Ka2, Ka3. You'll have a different equilibrium for each H plus that pops off. But again, we'll talk about that more next week. Just a heads up if you look at the table. That's all that was. So, what can we say about this? Well, acids have different strengths. On one end you have strong acids, right? Just release all their H plus. And then over here you've got stuff that just doesn't release H plus at all, like, I don't know, like, sugar or something. Sodium chloride just doesn't affect the pH really. And then in the middle, you've got your weak acids. And so there's a whole world of gray. There's stronger and weaker acids that are still under the umbrella, bear with me with the language here, of being a weak acid. Alright? So a weak acid can be stronger, meaning it generates more H3O plus, but not a strong acid, if that makes sense, where it generates all of the H3O plus that it can. So there has to be that equilibrium process, so there's the reverse reaction still happening. So what we can say in terms of that, if you're still with me and not confused, is that as Ka gets larger, we're going to have a more top-heavy ratio here. It means our acid is going to be stronger because we're making more H3O plus. So as Ka increases, an acid is considered to be stronger. Okay? And it's not that, Ka is changing for a specific chemical. You look up the value in the table, that's the value. But if you were to compare, say formic acid and acetic acid, you could look at the Ka values and see which one is stronger. Which one is going to give you a more acidic solution mole for mole. That's what I'm talking about. So when I say stronger, I mean that more H3O plus is generated. Alright, and so, you know, if you were to take this idea and apply it to like a strong acid, just as an example, you would have only stuff over here. So you'd have everything up here, nothing down here. Ka would go to infinity, which the whole idea is broken anyway, right? Because there's no equilibrium. But that's as strong as you could get. So an infinite Ka gives you the strongest acid possible. So as you get larger and larger values, more and more towards infinity, the stronger the acid is. The smaller and smaller it is, you know, maybe it's 10 to the minus 6. Okay, that's a weak acid. 10 to the minus 10, that's an even weaker acid. Okay? So, the other way of looking at, so this is one way of looking at the strength of an acid, is you just look at Ka. The other thing you can do is look at percent ionization. And so percent ionization is essentially just a measure, it's percent, so guess what, you're going to multiply by 100% in this formula. But it's a measure of how much H3O plus do you get for the acid you start with. You know, maybe it's a solid you dissolve, how much H3O plus are you going to get? 100% ionization, strong acid. Less than that, weak acid. 0% ionization, not an acid at all. Alright? So, those are our boundaries. And the way we calculate it is you take your equilibrium concentration of H3O plus, so you do like, I don't know, say an ice table to find this. You would divide it by the amount of the HA that you started with, the undissociated acid. So the initial amount versus the equilibrium amount. So both units of concentration, and then you just multiply by 100%. Okay? And so that's one way. So, you know, a middle of the road weak acid, which actually would still be considered pretty strong for the most part, would be like 50% ionization, right? That's actually still very strong. That'll shift the pH quite a bit. But a lot of weak acids will be like 1% ionization or less. So they don't make a lot of H3O plus. Alright, so yeah, that's what Ka is. It's just KEQ for an acid process. And so this is very general. It's not specific. I will make sure to be more specific in the practice sheet, but that way you can take this idea and pattern it onto specific systems, which will all be pulled from the back of your textbook. I'm not going to look up another table. So if you wonder where I get my Ka values and stuff like that, there's a table of them in the back of the book. So next we're going to talk about weak bases. And it's going to be a very similar conversation to the one we just had. And then what do you think we call K for this? What do you, take a guess, take a guess. What do you think? What do you think? Huh? KB, right? So KEQ for weak base systems gets known as KB. B stands for base. Alright, you got Ka and B on top of KW and KC and KP and KQ, all of which are equilibrium constants. And then you also have, if you go way back, do I dare mention it? The K's for kinetics. Because you can't spell a constant without K. Alright. So, here's our general formula here. You might be able to take a guess at it. We've got B, and I want to be clear, alright, this is not boron. It's not the most unfortunate element on the periodic table. B stands for base here. Plus H2O. It's a weak base, so we get an equilibrium. That is probably the most beautiful equilibrium arrow I've drawn since we started. There's a little lack of symmetry there, but not bad. That's almost textbook worthy. I just had to call that out. I'm very proud of that. Which means everything I draw from now on will be garbage. Let's see, so we've got a base, so what's it going to do? It's going to pick up an H+, and so that means we've got HB+, which is aqueous. If it takes that away from water, what do we get? OH minus is what remains behind. And so we have a base generating OH minus. That's what they do. So, what's our expression for Kb look like? Well, again, it's just the products over the reactants. Water's not going to factor in because it's a liquid. And so it'll be concentration of Hb plus times concentration of OH minus, all of which is over concentration of B. And again, this would be a number. There's another table in the back of the book. You can look up Kb values as well. So, yeah, for the worksheet, guess what I'm going to do? Guess where I'm going to go to get Kb values if I want you to compare them or something like that. Alright, so when we talked about acids, I'm serious, it's like almost the exact same script, just for all the A's become B's. All the H3O pluses become OH minuses, basically. There's one little detail to talk about. Well, no, actually, I'll talk about that later, so I don't have to worry about it now. So what does it mean for Kb? Alright, well, what does it mean for like the strength of a base, right? So as Kb increases, what does that mean? Does that mean a base is going to be stronger or weaker? And so for a base, more OH minus generated equals stronger base. So a strong base would be something like, a metal and a hydroxide. So like sodium hydroxide. Be a metal ion and a hydroxide ion. That's a one-way ticket. It does not reverse. You just get OH minus over here. You get 100% ionization. Oh, I've tipped my hand for the end of the section here. But as Kb gets larger, we get more top heavy. We get more OH minus, less just the weak base by itself, unionized. So it's considered stronger. Just like before, as Ka got larger, an acid was considered stronger. As Kb gets larger, a base is considered stronger. And in the case of a base, stronger means more OH minus has been generated. And again, it's not that Kb changes for a specific chemical, like ammonia has a value for Kb. But something else, another, like pyridine or something like that, another weak base, would have its own Kb, and you could compare those and say which one is the stronger base or the weaker base, that type of thing. And then, another way to talk about the strength of a base is, seriously, same script, basically. Percent ionization, alright? So what is the percent ionization formula going to look like for a base? A little bit different. It's going to be very similar, right? So it's still going to be our initial amount of the concentration of the base that we started with. But we don't want H3O plus at equilibrium. We want OH minus. Times 100%. So you have to do an ice table to get this. This should be given to you. Like I make a 3 molar ammonia solution. I put enough ammonia into water to make it a 3 molar solution. And I could ask what's the concentration of OH minus going to be, and then what's the percent ionization. I can do all of that. It's going to involve an ice table. And we'll talk about that in the next couple videos as well. Now, the last thing I'm going to talk about here. This is a key one, and I've hinted at it a little bit. But the strength of these conjugate acid-base pairs. There's a relationship here. So, if you have something like this, if you have a weak acid, you have the following system. here's our weak acid. And so what's this right here? Well, we could also say that this is our conjugate base. And if it wasn't clear before when I introduced what a conjugate base was, maybe if I say it again, maybe it'll make sense this time. So if we look at the forward reaction, HA acts as an acid. It releases an H plus onto H2O to make H3O plus, and what's left behind is A minus. That's the forward reaction. So that's as we go this way. If we look at the reverse reaction, what's happening with A minus? It's picking up an H plus and becoming HA. It is removing an H plus from the hydronium here, turning it into water, and then A minus becomes HA. So it is acting as a base. It is absorbing an H plus. So that's why we call it a conjugate base. So there's the acid in the forward reaction. There's the conjugate base acting in the reverse reaction. Now, there's a relationship here. As the strength of HA increases, if this becomes a stronger acid, the conjugate base is going to be a weaker base. The more easily this is going to dump off an H plus, the worse this is going to be at picking up an H plus. It's not going to want it back. All right. So if A isn't hanging on to an H plus very well, it's acting as a stronger acid. But if I don't know if you can hear my dog outside barking, but that's really annoying. There must be something going on. I think it's recycling truck day. The great recycling monster is driving around the neighborhood. It must be battled with her voice, her powerful voice. God, I can't, stupid lovely, I can't even think. That should scare her and quiet. She won't know what that was. Alright, sorry about that. What was I saying? Oh, okay, so I kind of hope the microphone isn't picking it up, but I kind of hope it is so that you don't think I'm insane. Alright. So there's like an attraction between our counter ion here and that H plus that's going to pop off. The stronger this attraction is, the harder it is to pull these apart, the weaker the acid is going to be, because it's going to be less likely to release that H plus. It's going to be more here and less over here. It's going to be shifted this way. Now, if there isn't as much of an attraction, then you're going to more easily pop off that H plus, which means you're going to be more over here. And if there's not much attraction, there's going to be less A minuses grabbing H pluses back and shifting right. And so, just to circle back, what it boils down to is, as the acid gets stronger, the conjugate base gets weaker. Okay? So, and the converse is, the opposite is true, conversely. So, if the acid gets weaker, the conjugate base gets stronger. Alright, so there's this relationship. And guess what happens with weak bases? So if we look at weak bases, right, old hat, you've seen this now for like 5 minutes. We get the following. And so we have a weak base. And so guess what we call this? Well, if a weak acid has a conjugate base, a weak base, is going to have a conjugate acid. So that's what's going on there. So, our base is absorbing an H plus. It's taking it from water, making OH minus, giving us HP plus. Now if we look at, then that's in the forward reaction. Now if we look in the reverse reaction, HB plus is going to donate an H plus to make water out of OH minus, which means it's releasing an H plus to become just regular old B. which means it's acting as an acid. So we call it a conjugate acid because it's on the product side. So this is a weak base equilibrium. So there's a conjugate acid. Just like we have a weak acid equilibrium, it's going to involve a conjugate base on the product side. Alright, and so what do you think happens as the base gets stronger? What happens to the conjugate acid? There's a really good clue up here. Okay, so it's also going to get weaker for all the same reasons that I talked about before. So as the base gets stronger, that means that our conjugate acid gets weaker. Alright, so that, you just look at where the equilibrium is. And so if you have a bunch of HB plus, that means that you have a stronger weak base. I know it's weird in the language, just bear with me. So you have a weak base that is relatively strong, which means that this conjugate acid is going to be very weak because it's not going to be donating H pluses very easily. It's going to be hanging on to them. And so there's that. It's just like the pH and the pOH. There's a balancing act here. If the base gets stronger, the conjugate acid gets weaker, or vice versa. Just like up here, if the weak acid gets stronger, the conjugate base gets weaker, or vice versa. All right, so that introduced Ka, Kb. We talked about our relative strengths of conjugate acids and bases, and it's not something that I expect you to bring numbers into. It's just kind of a general conceptual thing, which means that you despise it because there's no equation to just solve. You'll just have to kind of like understand the equilibrium, recognize the balance that's there. There's kind of like a pushing and pulling force here, and you have to kind of see how that comes into play. But don't worry, because for the next 2 videos to close out the week, we're doing math, okay? We're going to calculate pH of weak acid systems, we're going to calculate pH of weak base systems, and I'll show you, numerically an example of each percent ionization as well for weak acid and weak base. So that'll be what we do to end the week here. So if you're watching this and you're like, I want numbers, numbers, give me numbers. Don't worry, they're coming. Alright? Just hang in there. And if you're like, no, not numbers, sorry, I hope you enjoyed the conceptual stuff. So we'll do weak acids next. We'll do those first.